Today I'm going to be explaining common Pulley problems. For the first situation, we have an edge, and sitting on that edge, there's a mass m1 connected to a string that passes over a pulley to a second mass with mass m2. So to find the tension and the acceleration, we first draw the free body diagrams. So for m1, there is the force of gravity pulling the mass down, the normal force pulling it up, and the tension pulling it to the right. For the second mass, m2, there's the gravity pulling it down and the tension pulling it up. So using these diagrams, we're going to write our equations. For the first mass, we have T equals m1a, and for the second mass, we have m2g minus T equals m2a. And these are the same acceleration because they're connected by a tight string. And it's also the same tension. So by adding these two equations, we get m2g equals m1 plus m2a. And solving for this, we get a equals m2g over m1 plus m2. And now we can plug this back into the first equation, t equals m1a, to get t equals m1 and m2g over m1 plus m2. Now for our second example, we again have a pulley, this time with no edge. And on one side of the pulley, there is a mass of m1, and on the other side, the mass is m2. So there's the tension forces again. So now we'll assume that m1 is greater than m2, and it doesn't actually matter if you assume m2 is greater than m1, you'll just get a negative result if it turns out that m1 is actually greater than m2. But no matter what, you want to keep things consistent when you're writing the equations. Now we'll draw our free body diagrams. So m1g, on m1, the force of gravity and tension are acting on it. And for m2, again, gravity pulling it down and tension pulling it up. So now from these free body diagrams, we'll write our equations. So for the first mass, m1g minus t equals m1a. For the second mass, t minus m2g equals m2a. So adding these, we get m1 minus m2g equals m1 plus m2a. And from here, a equals m1 minus m2 over m1 plus m2g. And by plugging this back in, we get into the first equation, we can get t equals m1g minus m1a. And that gives m1g minus m1 times m1 minus m2 over m1 plus m2g, which is equal to, we're going to put it under a common denominator, and then we can cancel out the m1s. So this is 2, t is equal to 2 m1 m2 over m1 plus m2g. So now for our third situation, we have a wedge with angle theta, and sitting on that wedge is a mass m1 connected to a string that passes over a pulley, and m2 hangs from the same string. So we can draw the free body diagrams as usual. So for m1, there will be a tension force pulling it diagonally upward, and there will be the force of gravity, which we can split into components in the direction of and perpendicular to the wedge. And so m2g cosine theta is the perpendicular portion, and m1g cosine theta, not m2. And m1g sine theta is pulling it to the left, and then there's the normal force pulling it upward. And for M2, tension is pulling it upward, M2G is pulling it downward, and again we can assume M2 is moving downward, so this gives us M2G minus T equals M2A, and T minus M1G sine theta equals M1A. And since N cancels out M1G cosine theta, yeah. So then adding these two equations, we can solve for A again, and then we can plug it back in and solve for T. So T is M1G minus M2A, which is M2G minus M2 times M2 minus M1 sine theta over M1 plus M2G. And then we'll put this under a common denominator, which is, so we multiply top and bottom by M1 plus M2. And now the M2 squareds get canceled out. So the result is M1 M2 times 1 minus sine theta, 1 plus sine theta over M1 plus M2G. So here you can see that it matches the equation we got for the first situation in which theta is 0, as well as the second situation in which theta is 90 degrees, meaning there's no wedge at all. That's it for pulleys. Hope you enjoyed this video and learned something.